Electrochemistry, Part 2, Galvanic and Electrolytic Cells. In this video, we will look at the relationship between the physical components of an electrochemical cell and the overall operational principles of the cell. So let's look at the balanced redox reaction we considered in the last video. If we mix these reactants together in one beaker, it will get warm, but we won't generate any electric current from the flow of electrons. But if we separate the two half reactions into their own compartments and connect them with a wire attached to a pair of inert metal electrodes, like platinum, well, then we'll be on our way to making an electrochemical cell. If we do all that, however, it still won't work. There will be an instantaneous flow of electrons, but then it will stop immediately. Electrons will flow from the iron 2 compartment into the permanganate compartment, but then the left beaker will have an excess negative charge which will repel any further electrons flowing into that compartment. A rather simple solution is to connect the two solutions in such a way that ions can flow into them and keep the net charge of each compartment at 0. We can add a salt bridge, like the hastily scrawled one that I drew, using a U-tube filled with an electrolyte paste. This will allow charged cations and anions to flow into the compartments, keeping each one at a total charge of 0. Now we've got ourselves an electrochemical cell. Specifically, we would have constructed what's called a galvanic cell. A galvanic cell is a device that converts chemical energy into electrical energy using a thermodynamically favored oxidation-reduction reaction. Another name for a galvanic cell is a voltaic cell. If we wanted to reverse the reaction, we would need to force the reaction in the direction that is not thermodynamically favored, but we would need to apply an electric current of our own. This would convert electrical energy into chemical energy, and that kind of electrochemical cell is called an electrolytic cell. Anyways, let's take a look at the two components of an electrochemical cell. I'm sure you remember that Leo goes grr, but did anyone ever tell you what color Leo is? Leo is a red cat. That's a mnemonic device to remember that reduction occurs at the cathode. The cathode compartment of an electrochemical cell is the cell where the reduction half reaction occurs. Electrons will always flow into the cathode, because grr, gain of electrons, is reduction. The anode compartment of an electrochemical cell is the half cell where oxidation occurs. Electrons will always flow out of the anode, because Leo, loss of electrons, is oxidation. Electrons will always flow from the anode into the cathode. Leo goes grr, and Leo is a red cat. Reduction occurs at the cathode. Now let's say we want to construct a galvanic cell using the redox reaction we've been discussing. So we've got our hydrogen ions and permanganate ions in the left compartment, and we've got our iron 2 ions in the right compartment. There are some spectator ions in each compartment, but they aren't going to be involved in the reaction, so I shan't mention them again. It would be impractical to just stick a wire into each cell because the wire would quickly corrode and react with the half cell components. So we're going to connect the wires to an inert metal electrode, made out of platinum, for instance, to connect the two half cells. We'll also add a salt bridge of some rando ionic compound that will keep charges from building up in each half cell. The voltmeter will measure the electric potential of this cell, but we'll get into that in a minute. Alright, let's apply what we know and see if we can't label all 5 things listed here on our diagram. The anode is where the oxidation occurs, and iron 2 is being oxidized to iron 3. So the right half cell is our anode compartment. That means the left half cell is our cathode compartment. Reduction occurs at the cathode, and as we saw in the last video, manganese is going from a +7 oxidation state to a +2 oxidation state. So that's the reduction. Now, which direction are the electrons going to flow? Anode to cathode or cathode to anode? The electrons in this cell will flow from the anode to the cathode. Recall that iron 2 is losing electrons, oxidation, and manganese is gaining electrons, reduction. Electrons will always flow from the anode to the cathode in an electrochemical cell. So now let's focus in on that salt bridge. The salt bridge will allow cations to flow into whichever half cell is gaining electrons to balance the charge, and it will allow anions to flow into whichever half cell is losing electrons to balance the charge. So, into which half cell will the cations flow? And what about the anions? Since the cathode is gaining negative electrons, cations will need to move from the salt bridge into the cathode to prevent the buildup of negative charge. Cations into the cathode. That's convenient. Since the anode is losing negative electrons, anions will need to move from the salt bridge into the anode to prevent buildup of positive charge. Anions into the anode. Get it? Good. Now let's get quantitative. The pull on the electrons in an electrochemical cell is called the cell potential, or the electromotive force. We'll use a capital E or capital E naught under standard conditions to represent cell potential. The potential is measured in joules of energy per coulomb of charge, which is known as a volt. We will use a device called a potentiometer or a digital voltmeter to measure cell potential in the laboratory. Every redox reaction, and therefore every galvanic cell's reaction, can be written as the sum of two half reactions: the oxidation half reaction and the reduction half reaction. Therefore, the total cell potential for an electrochemical cell is the sum of the potential of the anode half reaction and the cathode half reaction. Let's take a look at an example. Let's determine the standard cell potential for a galvanic cell for the oxidation of zinc metal by acid. The anode, oxidation, half reaction, will be zinc forming zinc ion and 2 electrons. The cathode, reduction, half reaction, will be 2 hydrogen ions and 2 electrons forming hydrogen gas. In order to get everything under standard conditions, we'll have to have the anode compartment with zinc metal electrode and a 1 molar zinc ion solution. The cathode will contain 1 molar acid solution using an inert platinum electrode surrounded by hydrogen gas at a pressure of 1 atmosphere. This specific electrode is known as the standard hydrogen electrode, and it is the standard by which all other half reactions are compared to determine what are known as reduction potentials. But more on that in a moment. Remember, in order for this to be under standard conditions, all the reactants and all the products must be present in their standard states, which is what we've done here. The experimentally determined anode cell potential for zinc oxidation to zinc ion is positive 0.76 volts. Since the standard hydrogen electrode was used for the cathode compartment, it will have a cell potential of 0 volts. The sum of these two is the total galvanic cell potential, which is positive 0.76 volts. That's the sum of the anode potential and the cathode potential. Let's look at another sample problem. Our goal is to determine the cell potential under standard conditions for a galvanic cell that uses these components. The data we are given are the reduction half reactions and what are known as the standard reduction potentials for the half reactions. Now, in an oxidation-reduction reaction, something is going to be oxidized, so one of these half reactions is backwards. We'll need to figure out which one. The one that is backwards will be flipped, and the sign of the potential will flip as well. And the one that will be flipped is the oxidation, and that's going to go in the anode. So how do we know? Well, for a galvanic cell, the half reaction with the more positive reduction potential is the one that's going to go in the forward direction. So the more positive one for a galvanic cell is the one we're going to leave alone. The less positive one for a galvanic cell is the one we're going to flip, and it's going to run in the other direction because it's going to be oxidation. Since we flip the reaction, we'll flip the sign too. So, which one will go in the cathode and which one will be flipped to run in the anode? Let's flip the zinc half reaction. There we go. Now we've got a reduction half reaction for the cathode, that's the copper one, and an oxidation half reaction for the anode, That's the zinc one. Since the electrons will cancel out when we sum the reactions, we won't need to do any multiplying of the half reactions by integers to get the electrons to the least common multiple. But if we did, we would not multiply the half cell potentials as well. Cell potentials are voltages, which are energy per unit of charge. So they are intensive properties that do not depend on the amount. Anywho, let's sum the reactions, the half reactions, and sum their potentials. Now we have the balanced redox reaction and the standard cell potential for this galvanic cell, positive 1.10 volts. Since it's a positive cell potential, we made a battery. We can use this chemical reaction to produce electrical energy. That's a galvanic cell. Let's take a closer look at this galvanic cell. Here we have the galvanic cell constructed. Notice that it is a standard cell because the anode has 1 molar zinc ion and a zinc electrode, and because the cathode has 1 molar copper-2 ion and a copper electrode. Since zinc will be oxidized to zinc ion, as time goes on, the zinc electrode will lose mass, and since copper-2 will be reduced to copper, the copper electrode over time will gain mass as copper ions are plated out onto the copper electrode. By the way, as this cell runs, the concentration in the anode will increase and the concentration in the cathode will decrease. That means it won't be at standard conditions anymore. In fact, the cell potential will slowly drop all the way, eventually, to 0, and it will no longer produce electrical energy since the potential will be 0. In that case, it will be a dead battery, and that's what we would call it at equilibrium. But more on that later. Now let's take a look at the same components, but we'll use them to make an electrolytic cell instead. Recall that the electrolytic cell will run in the direction that is not thermodynamically favored, so it will run in the opposite direction that the galvanic cell would. So, which of these two reduction half reactions do you think will flip to make it oxidation? Recall that in a galvanic cell, the more positive one is the reduction, so we flipped the less positive one. This is an electrolytic cell now, so we'll leave the less positive one alone. The more positive one will be the oxidation. So the copper half reaction will be flipped and the potential sign flipped too. After we run the numbers, we'll get a negative 1.10 volts for the cell potential. Since this is an electrolytic cell made out of the same components as our previous galvanic cell, we certainly would expect to have a negative 1.10 volt cell potential, since the galvanic cell had a positive 1.10 volt cell potential. Anyway, this negative cell potential means that we'll need to supply an electric current with at least a 1.10 volt potential in order to drive this reaction in the non-spontaneous direction. We didn't make a battery. We made a copper-consuming zinc maker. We'd have to use electrical energy to drive this chemical change, but that's an electrolytic cell for you. Here we have a comparison of the two cells we looked at using the same chemical reaction, just in opposite directions. The galvanic cell has a positive cell potential, and the electrolytic cell has a negative cell potential. For the galvanic cell, the more positive reduction potential became our cathode, but in the electrolytic cell, the less positive reduction potential became our cathode. That means that when looking at the reduction potentials, the one you end up reversing will always end up in the anode. Notice that the electrons will always flow from the anode to the cathode for either cell. Notice also that the cations in the salt bridge will always move into the cathode, and the anions will always move into the anode for either cell. As we did on these sample problems, we will often start with a list of standard reduction potentials, like the large one in the appendix of your textbook. When looking at the two reduction half reactions for an electrochemical cell, keep in mind the following. First, one of them will always have to be reversed, changing the sign of the potential. If it's a galvanic cell, reverse the least positive one. If it's an electrolytic cell, reverse the most positive one. Second, if you are interested in getting the balanced equation for the redox reaction, you'll need to get the two half reactions to add up in such a way that all the electrons cancel out. since the number of electrons lost must equal the number of electrons gained. The half reactions must be multiplied by integers, as necessary, to achieve a balanced equation. However, the value of E naught is not changed when a half reaction is multiplied by an integer. The only thing you can do with E is to change its sign for the anode oxidation reaction. In this video, we looked at the components of a galvanic and an electrolytic cell. We also looked at how standard reduction potentials and half reactions can be used to determine the cell potential for an electrochemical cell. I think that's enough for now, don't you?